right, welcome everyone to the PARC Innovation Flow Podcast. Thanks for being here today. The PARC Innovation Flow Podcast is where we talk about PARC projects, research, technology, innovations going on in the wastewater space. And today we have a great innovator, a great wastewater innovator with us, Andy Safulko from Brown and Caldwell. And Andy is the national, I want to get this right, there's a lot of words, national technology leader, site investigation, remediation, and solids waste at Brown and Caldwell, but we kind of know him around here as the PFAS guy, and he's here to talk a little bit about PFAS research that he's been doing. Thanks for being here today, Andy.
Thanks for having me, Blair. Excited to be joining you.
Yeah, I'm glad you can make it in. I've been looking forward to talking about biochar, PFAS, all of it. So before we get there, could you just tell the listeners a little bit about your background, where you came from, where you're going, and some hobbies that you like to do?
Sure. Yeah, I'll try to truncate my life story here.
Yeah, we need it quick.
Yeah. My name is Andy Safulko, environmental engineer at Brown and Caldwell. I am the National Technology and Innovation Leader for our site investigation, remediation, and solid waste practice. Did my undergrad at CU Boulder, did my graduate work up the road here at Colorado School of Mines. And that's kind of where I cut my teeth on PFAS and kind of have been focusing in that area ever since. My background is largely in that site investigation and remediation space, but as PFAS has cut cross-sectionally across the environmental space and industry at large, it's provided me an opportunity to kind of spread my wings and get involved in some other areas and supporting our municipal clientele and wastewater and drinking water and water reuse applications as well.
Yeah, it seems like you've grown with PFAS. It seems like was that where you first heard about it? Is in school, or was it around before then?
Yeah, so I was kind of tracking PFAS as an emerging contaminant for a while, and then in 2019 I took a consulting sabbatical and went back to graduate school with the whole focus of really honing in and focusing really on PFAS and applied PFAS treatment technologies at Colorado School of Mines, which happens to be a nationwide leader in PFAS-related research that's in our backyard. So
cool.
It worked out, and then after I wrapped that up, did my research, my thesis, joined Brown and Caldwell, and got involved with some of the stuff that we're doing here at South Platte and PARC.
Nice. So you took a sabbatical and you chose to go back and get a graduate degree in engineering, huh?
That's right. That's right.
Seems like there's so many choices there.
Yes. Yeah. Exactly. A bit of a glutton for punishment, but I've always enjoyed school, so it was nice to get back into the academic setting for a little while and have definitely a more flexible schedule.
Yeah. Was it different going back as a non-traditional grad student than when you were in CU?
Definitely, yeah. I would say that had a different level of focus on round two.
Yeah.
But I was definitely the elder statesperson in my research group. Had a lot more gray hairs than most of my cohort, and brought a different perspective. I would recommend for folks that have maybe been considering going back to graduate school and are sitting on that. Maybe they're thinking they're past that point in their life. I found it to be really, really valuable and really rewarding, and would recommend it to anybody that's considering it. Yeah,
I found the same thing. I went back after I worked for a while, probably 5 or 6 years, and then went back, and it's different because you know about the industry. You're more, like you say, you're more focused on the issues. You're more disciplined, I think, and it's just a whole different experience. But well, cool. What about hobbies? What do you like to do when you're not doing remediation and investigations?
I like to do a lot of the typical Colorado things. I like to spend time outside, spend time with my wife and my dog. I'd say probably my single biggest hobby is fly fishing. So I enjoy fly fishing here in the watersheds up and down the Front Range of Colorado, and occasionally make a trip outside the state somewhere to go fly fishing.
Nice. How long have you been doing that?
I've been fly fishing 20 years now. Yeah.
Cool.
Yeah. Still not any better at it than the day I started, man. It's a real craft. I haven't graduated at tying my own flies and all that stuff, but yeah.
Cool. Yeah, I was at a a brewery a few weeks ago, and there was a fly tying club there, and there was all these old guys tying flies on this equipment. It looked pretty cool.
Yeah, special group of people.
Yeah,
You know, yeah.
I thought I should get in there. I don't even fly fish, but those guys look cool.
Yeah.
All right. Well, how about the interesting question here I got for you? If your job was made into a reality TV show, what would it be called? What would be the name of that show?
Well, I guess if I was going to maybe model it after an existing reality TV
I like
show,
that.
I would call it Survivor.
Nice.
And I guess maybe the reason why I say that is, there's certainly the kind of community aspects of it, maybe the political aspects of it. The challenges are different every day, just like in the show Survivor. And you never know when that blind side is where it's coming from next.
Oh yeah.
But I think maybe more than that, it's about like in engineering, figuring out how to do more with less. If there were no resource constraints, engineering would be a relatively straightforward task. But we're always bounded by some sort of condition, and so you're trying to figure out how to optimize that solution within those confines. And, I don't know, just the folks on Survivor, it's amazing what they can figure out how to do with a machete and a coconut. So,
Yeah.
yeah.
That show, I'm amazed how long that's been on. I remember when it first came out because we had a Survivor party. This was, I don't know how long it's been on, but a long time ago. And now you still see Jeff Probst. He doesn't look that much different either.
Yeah, whatever he's doing. It's all those coconuts he's eating, I guess. I don't know. Yeah, on the avocado diet or something. But yeah, he's aging well. And they've been getting after it for a while.
Well, cool. Well, let's get back into the not back in. Let's dive into the scientific. Let's start this podcast. We could talk all day about nothing, but let's talk about
our specialty. Yeah.
Let's talk about PFAS and the project you were involved in. But I think before we get to your project, for the listeners and viewers out there who don't know what PFAS is, maybe give a brief overview of what that even means.
Yes. PFAS is a acronym that stands for per and polyfluoroalkyl substances. So commit that to memory.
All right.
There's going to be a lot of acronyms in this time.
Yeah. And we're going to have you explain every one.
Yeah, perfect.
Okay.
All right, let me know. Let me know if I'm need to dive back in and do a refresh on any of the acronyms. PFAS, per and polyfluoroalkyl substances, is a class of synthetic organic contaminants. So synthetic meaning that they're largely man-made. There's very few examples, if any, of naturally occurring PFAS chemistries. And they were developed in the 1930s, 1940s, and kind of rapidly gained popularity in numerous applications spanning, commerce and industry and manufacturing, and in part because they do a lot of things really well. They can impart, specific properties onto products like oil and grease and water resistance. So in that capacity, they're typically applied to textiles and carpets, so raincoats. Scotchgard is a famous example of a PFAS-containing textile treatment. Food packaging, what your hamburger comes wrapped in, you don't want the grease to soak through that. So historically, those have contained PFAS. Also used in firefighting foams. Used by firefighters in fighting what they call Class B fires. So those are like flammable fuel fires. Mm-hmm. Anyway, big family of compounds that did a lot of things well and became really popular.
But
there's the big but. Yep. They really, in most of those properties that made them so popular, also contribute to some of the environmental challenges that they pose. One of those being that they're very stable in the environment. So they don't break down on meaningful timescales in the environment. So there's not a lot of that, kind of natural attenuation from that kind of breakdown perspective. Then you get into the toxicity side of things where the concentrations of concern in the environment through, potential exposure pathways to humans or other, ecological receptors are really low. So that's a new challenge, right? We're talking about parts per trillion concentrations of concern in PFAS, which is kind of new territory for us in the contaminant space. And then how mobile they are is another contributor. Once they get into the environment, because they're so stable, they don't break down. They end up circulating through our natural and engineered systems and accumulate in different areas and sources and sinks, and pretty much all the PFAS that has been released in the environment to date is still floating around out there somewhere, and we're working on trying to figure out ways to break that PFAS cycle, but that's really the challenge that our industry is facing, is that they're stable, they're mobile, and they're toxic.
Yeah. Yeah, as far as toxicity, a lot of them, they think they might be carcinogenic, is that right?
Yeah.
Those kind of things.
Yeah. And
health
so,
problems.
yeah, the whole family of PFAS compounds, right? We're talking hundreds, thousands, tens of thousands, maybe even millions, depending on how you define what is PFAS. But certainly some of the more well-studied PFAS compounds are classified as likely human carcinogens, so have that cancer endpoint potential as far as adverse health outcomes related to exposure.
Okay.
Yeah.
All right. Well, how about taking us a little bit about through your project, your research effort? I know it involved. First, I think we got to define these terms. It involved biosolids, right?
Right. Yeah.
So give us a quick once over on what biosolids are.
Yeah.
Then we'll tie them all together.
Sure, perfect. Yeah. We'll wrap our thread through this whole thing before we're done. Biosolids, so biosolids, you might, I'd welcome your take on what biosolids are. I'll give it a first pass, but we're certainly, I am not a conventional wastewater treatment person by background, so I'm starting to wade out of my my kind of technical comfort zone here. But biosolids are essentially, I guess it really starts with sewage sludge, right? Sewage sludge is the solid phase residual from wastewater treatment. And historically, there was a distinction between sewage sludge and then biosolids. Biosolids was the sewage sludge that underwent additional treatment to promote some sort of beneficial reuse. And historically, that's been land application. There's a couple of other examples of that. But nowadays, I think sewage sludge and biosolids kind of get used interchangeably. I think from a conversational standpoint, that when people say biosolids, they might be referring to sewage sludge at large. But anything I missed on that one?
Yeah, the whole sewage sludge. If you say that to a wastewater person, they're like, "What? What? We don't say that anymore."
See,
so,
there you go.
Yeah,
the rebranding
sludge.
effort. I missed out on that.
Well, sludge is like the raw stuff. So the stuff that you settle out. I think of that as sludge because it's raw, untreated. Once it goes in the digester, the bacteria worked on it for 30 days, converted. I mean, mostly that's dead bacteria. That's the byproducts of those reactions. And so it's really a whole. If you set a thing of raw sewage sludge, from the bottom of a clarifier next to biosolids, it's a world. There's two different products. So,
right.
Yeah. So I think that's the main thing. But yeah, it is. You're exactly right. The solids portion that's got to go somewhere, and a lot of it goes to fields as far as land application. Some of it goes to landfills at different places, or even incineration are the methods. But all right, and now we got biosolids out of the way. We got PFAS, and so how did you? What does your project involve?
Yeah, so I guess we can talk a little bit about the biosolids PFAS intersection first. So. Wastewater treatment facilities, municipal wastewater treatment facilities are, what we might call passive receivers of PFAS impacts, right? The wastewater treatment facility itself is not imparting any additional PFAS through, the treatment process at all. All the PFAS is coming into the plant from industrial dischargers, from people using PFAS-containing products in their homes, pharmaceuticals, floor wax, again, all these things, Scotchgard, all these things that, as PFAS worked its way into the consumer space. And so that PFAS comes into the plant, and PFAS within that family of compounds kind of spans a range of physical and chemical properties. Some of the PFAS prefer to be in the solid phase versus being in the liquid phase, so they'd like to be stuck to a solid versus being dissolved in the the effluent or the liquid portion of the wastewater. So when that biosolids residual is generated through the wastewater treatment process, there's a portion of that incoming PFAS that accumulates in that biosolids fraction. And as we get to know more about PFAS and the potential risks associated with them, that the land application piece, as a beneficial reuse alternative for biosolids has been threatened by the presence of PFAS. So we land apply biosolids because of the great nutrient value that they can impart in an agricultural setting, like a fertilizer. And boy, is that a great way to, as opposed to filling up our landfills with these materials, we can beneficially reuse them in a, agricultural setting.
Yeah.
But unfortunately, PFAS and the presence of PFAS in these biosolids is beginning to threaten the viability of land application because there's uncertainties regarding, okay, well, where does that PFAS go once it's been land applied in those biosolids? Is it getting into the groundwater? Is it, ending up in the crops somehow? And so there's some states have already looked at legislation. Some states have gone as far as banning the land application of biosolids, which is, a scary thing to consider.
Yeah.
And so that's what kind of gave rise to this research question, which I can go into now,
All right.
unless you want,
All right.
unless you
No,
had
I
any
think
other
now's the
things
time,
you,
yeah.
Okay, so we kind of set up right that PFAS and the biosolids intersection threatens this conventional land application approach. And I think check my numbers here, about 50% of biosolids produced in the United States are land applied.
Yeah, and I think part of it, just to throw in, I think the biggest threat is the unknown. I don't know, I don't think we've established that there's a harm to land application, but it's that whole PFAS is bad. We know some of it's in the biosolids, so and I think there's studies and people are looking at that. But I think, with a lot of things, biosolids, it's the unknown is usually what gets you.
Right, and that is the driver right now. I mean, I think again, some of these states have, for their own reasons, gone as far as the outright ban on land application, but in large part, the science is still developing. Our understanding is still developing regarding the potential risks here. So there's certainly not definitive risk out there in most areas, and that's an active area of study. So our research project really kind of looked beyond. Okay, so let's say that if land application is threatened, or just even exploring an alternative valorization of biosolids, alternative beneficial reuse that isn't land application, what might there be?
Yeah. And
how might it help with our PFAS problem?
I love that. I love the how might we do something different questions. Yeah.
So we teamed up with SPR and some other collaborators to evaluate how would biochar, that is principally derived from municipal biosolids, potentially be used to manage meet the typical biosolids management objectives, which are essentially disposing of those biosolids. Again, when you use them in land application, that's a beneficial reuse, but where that's not available, they use sewage sludge incinerators, like you were saying. They can send them to landfills. Mm-hmm. So if we look at those as management alternatives, if land application is off the table, or we want to explore something differently, what might we do? There's this concept of pyrolyzing the biosolids and making a biochar, and that biochar could have different beneficial reuse endpoints. And one that we evaluated was its use as an adsorbent, specifically as an adsorbent for PFAS.
All right.
So,
What is pyrolizing? What does that entail?
Yes,
If I want to pyrolyze something, what do I got to do?
Yeah, you got to talk to a guy. I got a guy. If you want to pyrolyze something, pyrolysis in general is a thermal process, and it's a thermal process at a relatively high temperature. So we're talking, there's a whole science that underpins pyrolysis, and there's a lot of variance and nuance to it. It can, how long you do it, the temperature. Yeah, exactly. We're not going to go into all that. But it's essentially a thermal process, 300 to 800 degrees Celsius in a next to zero or zero oxygen environment. So you're not combusting the actual material. You are using that thermal process to change its properties.
So it's not ash.
It's not ash. No, ash is more of a, you can take it to that ash endpoint, but a lot of the goal of pyrolysis applications is to end up with this biochar, which you can think of as like the charcoal that might be left over in your campfire.
Okay.
That stuff that's at the bottom that's kind of like not exposed to a ton of oxygen and just kind of simmers down there.
Yeah.
That's really what an analog to the process.
Okay.
And it's like a cousin of granular activated carbon, so you do a similar thing with granular activated carbon. You pyrolyze it. You take that feedstock, whatever you're going to use, if it's bituminous coal or coconut shell or whatever the feedstock is for the granular activated carbon. You pyrolyze it, but then you subject it to an additional step of activation, where you really get that like porous structure, and that those are more adsorbent oriented properties. Versus the biochar kind of ends at that pyrolysis process.
Okay.
And conventionally, biochar is typically used in land application, like a soil amendment. You can till it into the soil, almost like a land application kind of scenario, where it's not really imparting as much nutrient benefit, but it is helping with like the soil properties and making nutrients more bioavailable and things like that. Yeah.
So you said, can we take this biochar material and treat it PFAS with it?
Yes. Yeah. So it's like a killing three birds with one stone kind of situation here. Yeah. We were, two birds, not enough. We had to go with the three-bird scenario.
That's ambitious. I like that.
Yeah, certainly. It was, okay, can we manage the biosolids, right? So if we have PFAS impacted biosolids, you need to do something with it, right? And so let's just say under the scenario, Blair, if you couldn't land apply biosolids, what would be your plan B?
Plan B would, likely be composting, but if that was not an option, then landfill, I think, would be the next, because there's no incinerators in Colorado that I know of.
Right. And so then there's the whole landfilling thing is also like suspect or questionable at times, because one, there's a landfill capacity issue. So not all landfills are really set up to take all of a sudden that huge additional volume of biosolids. And then there's also issues related to actually landfilling the biosolids themselves, as far as their structural stability and what they might do to the landfill.
Yeah. And what it might do, I mean, like, it would just kill me, because it's like you have this highly dense, moist material full of carbon, nitrogen, phosphorus, all that the crops love: moisture, phosphorus, nitrogen, and you're gonna you're not gonna recycle it. You're gonna waste that and just lump it into, fill up a landfill so you can dig another one.
Right. Yeah. Exactly. Nobody wants a bigger landfill or a new landfill in their backyard these days.
Yeah.
So that is a strain on that system. So in the absence of those two options comes into pyrolysis, and some entities are challenged with this right now in the U.S. as far as can't land apply, can't landfill. What are we doing? Biosolids comes into play, or pyrolysis comes into play as an option to reduce the volume of those biosolids and stabilize them, right? So you're really, there's no pathogen risk. And in the process of pyrolysis and some of the stack gas treatments, the science is telling us that we're getting a lot, if not complete, PFAS mineralization, so PFAS destruction. So we're actually destroying the PFAS that's in those biosolids. And then we end up with this biochar product that can we then turn around and use that to maybe treat PFAS in the liquid phase at a wastewater treatment facility? So is there some sort of really great closed loop, elegant solution that we can, solve many of our problems with? So that was the ambitious goals of this study.
Yeah. What did you find? How did it shake out?
So what we found was that, so what we did, I guess I could set up the study. We looked at 3 biochars that, again, are principally derived from municipal biosolids. And I say principally derived because sometimes they mix in other feedstocks, like woody waste and things like that, because the feedstock that you use dictates in many ways the final properties of that biochar product. Okay. So sometimes they amend it with different things, because to be quite honest, straight up biosolids doesn't necessarily make the most ideal feedstock for biochar generation. So principally biochars principally derived from municipal biosolids. We had 3 of those, and we did an isotherm study, which is like a way of evaluating adsorption performance.
Okay.
And we benchmarked it against one granular activated carbon, kind of like the gold standard
Right.
for PFAS adsorption as far as like a carbon-based adsorbent is concerned.
What they used in drinking water plants
Yeah,
to take
yep.
it out. Yeah.
That's right.
Okay.
So that would be kind of, again, like the bar that, man, if we could get anywhere close to granular activated carbon performance in these, that would be a dream. And we looked at 3 different waters. We looked at a laboratory water, like an ultra pure water, where we spiked in PFAS concentrations of known quantity. Then we looked at treated wastewater effluent from your facility, and we also looked at a groundwater. And we ran this big, experimental matrix where we had all these different biochars and the GAC and all the different waters and different concentrations. And we ran this isotherm experiment. And what we found was that biochar does, in that capacity where it was, again, maybe not originally designed to be an adsorbent, it did have some significant PFAS adsorption capacity.
Oh.
Importantly, it also didn't leach in our controls. The biochar from the biosolids didn't leach any detectable PFAS, which was a good thing.
Yeah.
It did underperform the granular activated carbon, which we expected.
Yeah.
And it might not be a fair comparison, again, because the granular activated carbon is really engineered and designed to be an adsorbent in that capacity. The biochar, not so much, and then that kind of leads into maybe some of these future research efforts.
Yeah.
But in terms
It's
of
like you took like a rebuilt Datsun and compared it to a Ferrari. As a
exactly,
baseline.
you know what? Still gets you from point A to point B.
That's
though.
right. That's right.
So yeah, we in terms of like to what degree did it underperform? I guess we're still evaluating the data. It's kind of preliminary at this point, and we're writing up the paper.
Mm-hmm.
But orders of magnitude, unfortunately, I guess it in terms of 10 times, 100 times lower adsorption capacity relative to the GAC, but that doesn't tell the whole story in terms of how does this shake out against a granular activated carbon, again, because you've got this treatment residual in the form of the biosolids that you need to do something with anyway, right? So there really is a need for a more holistic life cycle assessment approach to better understand how does these biochars in an adsorption, kind of capacity compare to things like granular activated carbon.
Cool. So did you, or are you going to explore, maybe it doesn't work for, water treatment, drinking water treatment, wastewater treatment, but have you looked at applications it may be suited for, or is that part of the study, or where's the study headed from here, I guess?
Yeah, so I wouldn't go as far to say that like it won't work in those scenarios. I think it's just about figuring out how it might work.
Yeah.
And then there's other things like, going back to like using biochar as a traditional, soil amendment. Can we take that biochar that we've now generated and bring it to historical biosolids land application sites that might have residual PFAS impacts, work it into the soil, and help kind of, remediate those impacted plots, if you will. So those are all on the table. But I think really one thing that I'm personally interested in and direction we're interested in taking this research is how well can we do with the biochar from biosolids if we go into that pyrolysis process with the idea of generating a functional adsorbent, right? Like if we're like, we want to use this in adsorbent, there's a lot of different levers that you can pull in the pyrolysis process. And then there's all those activation steps that we do with granular activated carbon that impart those properties. And so looking at, are we optimizing around even creating the best possible adsorbent that we can?
Yeah, that's interesting. Yeah, so this is right at the beginning maybe of the research, and then if so you did it without trying to optimize, and now you're saying, what if we actually try to make the best possible thing we can?
Right.
How will that measure up to granular activated carbon?
Right. Because
Cool.
I think and there's many others at BC and outside of our organization that are much deeper experts in this particular area, but the traditional, where the few locations where we actually have operational pyrolysis units in the United States, it's not clear to me that the endpoint is actually generating a viable adsorbent. It's more about meeting those objectives of really reducing the volumes of biosolids residual that has to go to landfill, and breaking the PFAS cycle in the biosolids themselves by subjecting it to this destructive pyrolysis process. Yeah.
Well, that's interesting. Thanks for sharing your research with us. I think it's great, the whole using a waste or using, I guess, the problem to solve the problem.
Right. Yeah. Exactly.
Is interesting, and then just the whole, you've learned a little and build on it and build a little more and see what you can come up with as far as technology and scientific advancement. So yeah, that's awesome.
Yeah, and I'm I'll plug here that I'm a PFAS is really it's a big problem. It's not necessarily insoluble. I think we're gonna get there with solutions, but it is gonna take a community effort to get there.
Yeah.
And there's a lot of groups that are working on this particular aspect, in addition to all the other things that that PFAS challenges us with. But folks up at CSU, my colleagues Lloyd Winchell, John Ross, are looking, and in addition to many other groups, are looking at, okay, how can we help solve these issues, particularly again on that using the problem to solve the problem kind of thing in the biosolids pyrolysis space. And I am hopeful that we are definitely making great steps towards viable PFAS solutions.
Cool. Well, I'm glad we got you on the case. It sounds like we got the right man for the job.
I guess so. I don't know. Hopefully.
Can you? We talked about pyrolysis, biochar, those kinds of things. But I know Brown and Caldwell and you are involved in some other PFAS work. Can you give us a little, and I want to do a whole show on it at some point, but give us a little teaser, give us a little sneak peek into some other PFAS stuff going on around here.
Yeah. PARC has been an SPR, and the PARC Center have been a great research collaborator for us. We're currently working on a WRF-tailored collaboration to investigate using machine learning approaches to help with PFAS source identification, which again will help with that whole passive receiver issue, right? Mm-hmm. The wastewater treatment plants have really limited control of what's coming into their plant, and so they need to go and figure out, okay, who's sending them PFAS, and then how do we control it?
Yeah.
Using machine learning to really help identify those particular sources within the collection network and support those source control efforts. So that's one thing that we're actively working on. And then I guess that is in collaboration with some research partners out of the University of Oklahoma and our folks at BC. And then foam fractionation is a PFAS treatment technology that we're looking at. That work is being led by my colleague Andy Huff-Chester. And it's in the very early stages, but we're bullish on the concept of potentially being able to use foam fractionation at a meaningful scale in a wastewater treatment facility to potentially manage the PFAS impacts entering the facility. And the basis of foam fractionation is essentially introducing air into the PFAS impacted water and little bubbles at the bottom of a contactor, mm-hmm. and letting those bubbles rise up through the water column and collecting PFAS on their way up to becoming a foam.
Yeah.
At the top of the water column, you collect that foam, and it's significantly enriched with PFAS, and under the right circumstances, you can get to really low treatment levels with a well-operated foam fractionation system. And we're currently exploring the viability of this particular technology at the scale of a wastewater treatment facility, and
Cool.
its ability to manage PFAS in the complex wastewater matrix that is municipal wastewater.
Yeah. All right. Well, that's great. It's amazing how much work there is going on to solve the PFAS problem, and how many different ways people are coming at it from different angles. And it's good I'm glad that you came here to share a few of them with us today.
Yeah, I'm happy to be here, and always, I could rap about PFAS all day.
Oh, I know.
So you better cut me off. I don't know. We're probably over time.
We got to do the end of the show segment here before you go. So I told you I wanted to do some two truths and a lie. Did you bring a two truths and a lie with you today?
I did.
All right.
You don't know, but I might be playing two lies and one truth.
Oh, yeah? I don't know. All right, you want to
We'll
go
see.
first? You hit me with one, then I'll hit you with one.
Or
you want me to start?
You start.
Okay.
You start.
All right. Okay, this is PFAS related. Here's my three statements. Lululemon leggings contain PFAS. Tom's of Maine toothpaste contains PFAS. Household dust contains PFAS. Which
Wow.
one? Which is the
And
two
you really
truths?
cut right in my
Yeah,
heart there.
yeah.
man. What if I don't get this right? I will say, between the Lululemon and the Toms of Maine, I'm going to go with the Toms of Maine contains PFAS is the lie.
That is correct.
All right.
Although I just read, because I was looking this up, because Tom's of Maine is supposed to be all natural.
Yeah.
It was like the natural toothpaste, but they are getting sued their mouthwash because they found PFAS in their mouthwash, which is also supposed to be natural, but they don't know if it's the bottling or what. But anyway, the toothpaste is not supposed to have any in there. But Lululemon, I get saturated with this stuff, so
Yeah.
sweat will just drip right off.
I
during
gotta.
yoga.
Yeah. I should reevaluate my Lululemon legging collection.
You should.
Yeah.
All right, what do you got?
All right. I went with some personal statements
Okay,
here,
all
so
right.
this is gonna see how well do you know me, Blair.
Okay,
All right. Here are my three statements.
let's hear it.
I grew up with 7 brothers and sisters.
Okay. Let me get my pen here. Go ahead.
I am the 1998 Erie County Watermelon Seed Spittin' Champ,
Oh, I like that.
and I once caught a 50-pound barracuda.
Oh, these are good ones. I'm going to go with... Wait, where was the watermelon champion from?
Erie County.
Erie County. If you even know the county, I don't know. That one sounds legit. I'm going to go with the barracuda. 50-pound barracuda.
And
No? What was it,
I
that
did catch that.
watermelon?
Yeah, it's the watermelon.
Oh,
speed.
man.
Yeah, you know.
Man, if you wouldn't have had the Erie County in there, I would have...
Yeah, I got specific on it. I
Yeah.
added that.
That was tricky.
It was yeah.
All right, I got one. And these all, I tried to do a liver theme for you.
Oh, yum.
I love to eat liver and onions. I've inspected thousands of cow livers, or the human liver performs over 500 functions. Which one of those is the lie?
You like liver and onions, the cow livers, and
The human liver
human
performs
liver.
over 500 functions.
I know I'm putting my liver through the paces. I think it's doing at least 500. I'm going to go with you like liver and onions.
That is correct.
Yeah.
Yeah, I wouldn't eat that stuff.
Yeah.
Yeah, no, but I did a little stint in the USDA as a food inspector, inspecting cow livers and cow parts.
What'd you find?
Wow, some of them are nasty. Most of them are good.
That's a
I
next.
got out of that game.
Yeah. Stay tuned, folks. We'll be back to learn more about Blair's time inspecting cow livers.
All right, you got any more? Or did you just had that one?
I just had the
Okay,
one.
I got one
I
more.
didn't come
I got
ready,
one
yeah.
more. Okay, there's a robot that inspects sewers that's nicknamed the sewer shark. These are just random. Dissolved air flotation tanks use tiny bubbles to lift solids up. Our operators at wastewater plants often use pool noodles to stir sludge in the digesters.
I don't know if you could stir much with a pool noodle.
You got that one?
I think I'm going to go with that one.
Yeah, that was too easy.
Yeah.
I thought you'd think that was real. All right, well, that's all I got. I think you hit them all, and I lost, so you're the winner.
Hey, that's thanks for being a great host and letting me win.
Yeah, that's what I do for the guests. You can collect your prize on the way out. But yeah, thanks for being here. This has been a great conversation. I look forward to having you back when more of that PFAS research of the foam fractionation or the fingerprinting as it progresses, and talking to you again.
Thanks, Blair. Looking forward to coming back.
For our listeners out there, thanks for listening to the Innovation Flow podcast. Thanks for sharing your time with us today. If you like the show, give us a 5-star review on Apple Podcasts or Spotify or wherever you're listening from. If you're watching on YouTube, be sure to like and subscribe to the show, and make sure you tell a friend, tell a up-and-coming School of Mines student or a USDA liver inspector or whoever you know about the podcast, and we'll see you next time. Thanks for listening to the Innovation Flow podcast.